Okay, welcome everyone. I'm giving a talk now, which I gave live in York in July 2024, and as usually, I decided to, or maybe not as usually, I decided to, instead of recording it live, just record it here in my little studio, which is a bit nicer because the quality is a bit better. Now it loses a bit the flavor of, well, the live action, I guess. But what can you do? So it was actually a really nice talk. We even had a fire alarm in between. Yeah, and then it was like, should we run? Shouldn't we run? Should we stay? Oh, it was a lot of fun. Eventually we ran. Right? We were not really running. It was false alarm anyway. But anyway, we went out, went in. It was a lot of fun. Hopefully this will not happen today, and I can make this recording without any interruptions. Anyway, I think the story is actually pretty nice, and I'm going to explain it like in this video. So as I said, I gave the talk. It was a lot of fun. We had a lot of interactions. This won't happen now, so because it's a recorded video, so there will not be any questions in between. But anyway, we go for it. So I would like to talk about equivariant neural networks. I will explain what those are or how I think about them. And yeah, as soon as you have some equivariance, there should be some form of representation theory addressing those questions, and this is based on work of those two guys, which ended up on archive eventually. And here you can see I gave this talk in July 2024, and depends now when you watch this video. I certainly recorded it much later because I'm just very lazy. Anyway, so let's go beyond linearity, and here you can already see kind of my thumbnail here. Something that is not linear. So whatever you see is clearly not a linear map, right? It's a piecewise linear map to spoil the story. But anyway, let's get going and let's see what we can say. So first of all, maybe I'm trying to recall for you what is a neural network, kind of in a nutshell. So it will be very brief and short and hopefully still make some sense. And we'll see what we will do with it. So kind of this idea of geometric neural networks, geometric AI, is a little bit to try to, well, explain the math behind AI, like ChatGPT or something, which is really difficult because most of the time, or mostly, it is actually like the brain. It's like a black box. We don't really know why it works. We can say certain things, but we don't really know why it works. And the whole point is, at least for me, to find some nice explanation, or hopefully some explanation, and get some nice mathematics out of it. So it should be a back and forth between mathematics and kind of deep learning, neural networks, AI, whatever you want to call it. And in my very, well, baby picture here, I think of a neural network. I have the task is to identify handwritten digits, whatever, zeros, ones, twos, you know what handwritten digits are. And so how do you model that mathematically? Well, let's say we can see this. I will zoom in a second. We can see this as a function. So every neural network should be a function. It's a very sophisticated function, but it's in some sense just a function. And let's say in this case, we can just convert our little pictures, our little handwritten digits, to a certain grid of numbers. Let's say grayscale. So let's say 28 by 28 is a size people use very often. And you flatten that into a vector, which really just means instead of having a 28 by 28 matrix, you just whatever read row-wise, and you get a vector with a lot of entries. Well, maybe not a lot. It's actually quite a small example here. With a certain number of entries, 28 squared entries. And so that's the input vector, right? The input vector is some of those flattened out grayscale images. And the output vector, what is the output vector? Well, the output vector should be what digit it is, so it should be a vector with 10 entries, right? So first entry for 0, second entry for 1, and so on. And so we have a function, I will zoom in a second to hopefully make more sense, from 700 and a real space 784 dimensional to a real space 10 dimensional. And why do I have real numbers? Well, I kind of think of everything as like a grayscale value is some value between 0 and 1. And in the end, my output vector should be like a probability of something being a 0, something being a 2, something being a 5, you know, something like this. So here in my little picture, I think of this handwritten digit 3. So I stole this picture from a really cool 3 blue 1 brown video on, well, neural networks. And it's really good explanation, much better than what I can do. But anyway, so here you can see how this essentially is supposed to work. You have my 28 by 28 grid, 28 by 28. As I said, I will just flatten it out. I have this thing, and I flatten that out into a vector, something like this. And every entry is a grayscale value. 0 is black, white is 1, and whatever. A grayish thing is 0.6 or something. So you get a real number valued vector on that corresponding 28 by 28 space, right? So I have my 28 squared space, and I get a vector in that space. And whatever, the output example could be something like this. Some spread of numbers, 0.100, whatever, blah, blah, blah. And this is like the probability that something is, whatever, a number 0, a number 1, a number 2, a number 3. And this is like my function from a high-dimensional space to a 10-dimensional space. So it's kind of some kind of form of function, which is the handwritten digit function. No, that's what it's supposed to be. And the whole point of a neural network is now to, well, that's a function, and in general these functions are like super difficult, and we don't know, they're not easy functions like x or log or a polynomial or something. They're really difficult functions, and we would like to approximate them, right? Approximate the unknown function. So a neural network is nothing else than an approximation to an unknown function. A very sophisticated one, because usually the functions are very difficult, but essentially that's what it is. And it is made of two ingredients. It's kind of surprisingly that it actually really works, but it's made out of 2 ingredients, which is a lot of matrices. I will zoom in a second for that for you. So linear maps. And yeah, so linear maps will not approximate a function. If you think about a function, here's a function, well, a nice function. And a linear map, well, let's say in black, will usually be, let's say, a tangent at a point. So at a point, this is really good, but in the overall picture, my black approximation on the green curve is like not good at all, right? So linear does not approximate a function well. So a neural network cannot survive without some non-linearities. Depending a bit on the function you want to approximate, just to say that clearly, if you have a linear function, I can clearly approximate that using a linear function. That's easy. So some neural networks actually can work without non-linearities, but in general you need them. Whatever non-linearities means is a bit of a matter of taste. So a popular one, which is not the most popular one at this point, of recording, there are many other variations, and whatever I'm saying today, you can do that with those variations as well. Just for this type of problem, we just focused on the piecewise linear, because the little bit of an extra step from linear is piecewise linear, something like my red curve here, and piecewise linear is then enough to approximate any reasonable function. And yeah, so that's a neural network, a bunch of matrices. Matrices because matrices are easy, but it's not quite enough because you want to approximate a function. Linear functions will not approximate a function, so you need some form of nonlinearities. And as I said, ReLU, my little function here, the one I'm going to use, is not the most popular anymore, but it's just ridiculously simple, so I'm going to use it anyway. So ReLU is just a function that is 0 on the negative part, and then the identity on the usual, the positive part. A really, really easy function. And this function is actually enough to approximate any function. And as I said, it's not the most used anymore. It was for some time, but it's certainly very, very beautiful due to its simplicity. It's a really, really easy function. And yeah, it leads me naturally to piecewise linear stuff because it is an example of a piecewise linear thing, right? It's not linear, but every little part here, so this little part is linear and this little part is linear. Anyway, so let me zoom in into the matrices to make this a little bit clearer. So a neural network in this usual description usually looks like this. You have some input vector, which was a 28 by 28 vector in our little example. And you have an output vector, which was 10. And then you might have some hidden layers in between. And they're really just a bunch of matrices. So every little picture like this, I will zoom in a second. So this is kind of a very, very vanilla and very, very tiny neural network. So there's a one-dimensional input space, there's a two-dimensional output space, and I go through a three-dimensional middle space. And that's essentially what a neural network is, and people draw that in terms of a little graph, where really each node represents a copy of R, and well, every edge represents a matrix entry. It will be more precise on the next slide. But essentially a neural network is then just a directed graph, and the task of a neural network is to approximate our unknown function. And I'm not going to explain how that works. This is backtracking, forward pass, backward pass, and a lot of gradient descent. But essentially, there is some process involved that adjusts the matrices until you approximate your function. Really, just exactly in the same way as you have some function, and there's some algorithm to approximate it piecewise linear. Maybe you just have a few points chosen, and your first approximation is pretty shit, and then you make the points a little bit finer, whatever, and your approximation gets a bit better, something like that. And then you just iterate the process often enough, and you will get an approximation of the function. It's just the neural network is just a really, really large thing. So ChatGPT will have billions of different matrix entries floating around. Okay, and people usually say the neurons are the entries of the vectors, and the weights are the entries of the matrix in the following sense. So here's my little vanilla neural network. So there's a 3x1 matrix XYZ, and there's a whatever 3x2 matrix here, A11, whatever, A13. A13 goes from 3 to 1, 1 goes from 1 to 1, something like this. And yeah, so a neural network is then a bunch of matrices, just every slice is a matrix, and a bunch. And then the function itself is just a composition of them. And by matrix, people in this business usually mean what mathematicians tend to call an affine map for some completely obscure reason. So everyone else calls it a linear map because it's just a line. Yeah, a line is a linear thing. But for a mathematician, because a line doesn't need to go through the origin, mathematicians call a line an affine map because there is some bias involved, the shift from away from the origin. Whenever I say linear map in this video, I stay with the reasonable terminology, so not the mass terminology. I will not call this an affine map because the line is linear. So matrix plus bias, that's a linear map. Say it again. Sorry, it's a linear map. Say it again. Mathematicians call that an affine map because of the funny bias, to shift away from the origin. But let's be realistic. A matrix plus a bias is just a shifted matrix, so it's still a linear map. Anyway, so that's what I call a linear map. So in the neural network, that's how it works. You have a lot of, every slice of the neural network is some matrix, and usually they have very large matrices, and the composition of that matrix is your approximate function. Up to the one catch that you need to throw in those nonlinearities. So here's a number before we go to the nonlinearities. Here's another example. So it goes from R3 to R4 to R3 to R3 to R2, and there are a lot of like matrices involved. Here's a matrix, here's a matrix, here's a matrix, and here's a matrix. So you have 4 matrices, and the composition of them is the corresponding approximation given by the neural network. And that's essentially what it is, but it's not quite true. It's just almost true. And the point why it's not true is that you need those nonlinearities. And what you do is at each, so you apply your matrix, then you usually apply a nonlinearity. You apply a matrix and nonlinearity, apply a matrix and nonlinearity. So this is how it usually should look like. And let's say in this video, my favorite nonlinearity is the ReLU function, right? Remember, ReLU is a very, very easy thing. By the way, some people call it ReLU, or some people call it ReLU. it doesn't matter. It is this easy thing here that's really like easy. So at every component you apply this one, at every step you apply that one component wise, then comes the next matrix. You apply it component wise, it comes the next matrix, and so on. And this brings in the corresponding nonlinearities into the game, where here's for this kind of the standard example is you have 2 point clouds, or an inner one red and an outer one blue and an outer one red, and you want to find the function that distinguishes them. And if you just have a linear function, what can a linear function do? A linear function can try to draw a line, like in this picture, and this is just not going to distinguish two circles because life is not linear. And with nonlinearities, piecewise linear, you can definitely just figure out that the best approximation onto a circle with a piecewise linear map is something like polygon. And yes, so if you run that in a kind of a very vanilla neural network, it will eventually find a polygon to distinguish the 2 points. And that's like the difference between nonlinear and linear, right? So in linear world, you can't approximate it. You can only draw a line. The line will not going to separate 2 circles. But in piecewise linear world, you can, and that's why we built them in, right? So piecewise linear, in nonlinear, piecewise linear in this video, we just have matrix, ReLU, matrix, ReLU, matrix, ReLU, matrix, ReLU. And then for ChatGPT is a little more sophisticated than this. It's like a vanilla neural network, what I'm going to show you. But let's ignore that. For ChatGPT, you just would have like a zillions of different matrices, which are really large, of really large spaces. So that's kind of a neural network. And our task is to somewhat apply techniques from rigorous mathematics to neural networks. And I'm a representation theorist, so maybe that's what I would like to apply. And we'll see how that actually works. But just keep in mind this mantra, matrix, ReLU, matrix, ReLU, matrix, ReLU. Yeah, very nice little mantra that comes up in neural networks. So what is now an equivariant neural network? Well, let's think about the problem. Very often, kind of a problem is equivariant under some symmetry, right? So if you have a kind of a point cloud of a flock of birds, then it really doesn't matter what bird is what. So you actually have a action of a symmetric group here, just permuting the birds. So there's an action of a symmetric group. Maybe you have something like ice cream recognition, a very crucial task in human history, ice cream recognition. And ice cream recognition, whether that, very crucial, but it's clearly somehow invariant under shift. So whether my ice cream is nicely centered or whether my ice cream is a little bit shifted left or right should not affect the result, right? So there's an action of z squared in this case, which just acts by shifting the picture in the 4 possible directions, right? Image recognition, that's what I just said, is often invariant, and the translation is the more fancy way of saying it. I would say ice cream recognition doesn't depend where your ice cream is in the picture. Speech recognition should be invariant under kind of when the speech appears in the recording, so it's invariant under time shift. Point clouds, problems of that form. There are like a lot of them, which actually have some symmetry built in. So in the language of mathematics, this means actually there's a group acting on that space. And whatever the neural network in some sense is then a representation of the group. Yeah, and I'm talking about what people here call symmetry in data. Yeah, I have my symmetry in data. I have some group acting on my data. I have some symmetry in the data, and we kind of want to see that in the neural network and then apply techniques from representation theory to our problem. Hope that makes some sense. Here's another example. So periodic image, which is really just my ice cream recognition, but you kind of put it on a torus, so you identify left and right and top and bottom, and you have this translation by a finite group in this case. See, I'm really doing this toy example here to bang everything finite. Instead of having z squared as before, I have now some finite group in the size of the periodic image, Zn, and the translation is just translate everything to the right, translate everything to the top. So here, this little corner, if you translate it here, it goes to here, and if you translate it in the other direction, it will go to here, right? It's like periodic. So if I shift it out of the top, I come in at the bottom, and whatever. So I have an action of the cyclic group, in this case, cyclic group squared. Yeah, so Zn squared, which makes it finite, makes it a bit nicer. Finite representation theory of finite groups is somewhat much nicer than representation theory of infinite groups. Just simplifying my problem here. And what I can really do now is and it kind of builds what I would call an equivariant neural network soonish. What I can do is I can think of a periodic image as a certain vector space, and really it's just a function from my periodic, this is maybe not an excellent color, so let's change colors, from my z squared, the n squared, cyclic group n squared, into the real numbers, where you just assign to each point its grayscale value, you know? And the usual action you have on a function space is exactly the shifting space. And now we are in business because we kind of related to mathematics that we know. So these representations of a group into the, let's say, real numbers, into the grayscale values, they are called permutation representations. And the standard notions from kind of representation theory that people have studied for 100 years, they apply here on this example of a periodic image, and they will in general. So maybe that's a good idea to call that thing an equivariant neural network. Well, makes some sense. So functions from Cn squared to R, which just really assigns to this whole block here a matrix of real numbers, which you should think of the grayscale values of my little picture. I hope it makes some sense. And then what is an equivariant map? Well, it could be, for example, a convolution operator acting on the picture. So here convolution by the element C, which is like the average over shifting left, shifting right, shifting top, shifting bottom, and it's kind of a convolution operator. And this is what people have studied in representation theory for a long time. There's like convolution operator on function spaces. This is a standard example, or the prototypical example of an equivariant map in this case. So I have permutation representations sitting kind of as a kind of a vertex, and equivariant maps are something like convolution operators on those spaces, which mimics this type of periodic image thing actually very, very nicely. And like convolution operators is what people usually apply for images. So kind of Gaussian, kind of these blur operators, sharpen operators. So really convolution is usually some little matrix, and you take some form over the neighbors and sum all of them up. So identity convolution doesn't do anything, of course. Here, your new node. So what I did is this one, where my new node gets the sum over the neighbors, the new value, and then I just normalized it by dividing everything by 1 over 4. But there are many other type of convolution operators that you could apply. So whatever, and this is really what you do in picture recognition. So actually this seems to be kind of a nice connection, as I said, between things mathematicians have studied for 100 years and things people do in kind of computer, picture image recognition in this case. So maybe that's how you would like to define an equivariant neural network. So this is how I define now an equivariant neural network. So we have some representation sitting on every vertex and some convolution operator sitting on every edge, which is definitely a little bit more complicated than the previous picture, where every vertex was just kind of a trivial representation, if you want, and every entry was just a matrix entry, and now just I blow it up a little bit, right? So as an equivariant neural network on a point cloud, you would have functions from 1 to n to r sitting in every vertex, and some equivariant convolution type operator at every edge, and then you again compose everything with the corresponding piecewise linear maps on in the composition. But otherwise, it's now a bunch of convolution operators that you collect in a matrix and a bunch of representation at every vertex. And this is kind of nice now, because all involved spaces are representations, whatever, of my acting symmetry, of my acting symmetry group, and all my maps are equivariant. So in other words, this is a standard problem, or this is a prototypical problem a representation theorists would usually like to study. Yeah. So we should be able to use representation theoretical methods to decompose, for example, our space into the irreducible or simple bits, into the elements, into smaller pieces. And that's essentially the representation theoretical questions I would like to address after setting up this notion here of an equivariant neural network built of some form of mimicking Fourier analysis, if you want. And again, there are non-linearities that you that needs to be built in. And this together studies, the neural networks are non-linear. So this together studies actually, it motivates the study of some beefed up form of representation theory. In this case, if I think about my little ReLU function, it would be piecewise linear representation theory. Yeah? I hope this analogy makes some sense, right? I want to decompose my network, which is like mimicked now, or kind of build on a mixture between what people have done in image recognition for all the time in Fourier analysis and in representation theory at the same time. So it looks to me like a good definition. And at the same time, I'm kind of forced to use a beefed up form of representation theory because my maps are not linear anymore. They're linear plus nonlinear, linear plus nonlinear. So I need some form of a nonlinear theory of matrix representations to study those. Hopefully that makes some sense. And in this video, it will be, because I'm using ReLU, remember this is this little thing, it will be piecewise linear representation theory. So let me show you what piecewise linear representation theory then actually is. Just using my example of the cyclic group. Right? Not just say with the cyclic group, we want to beef up representation theory and allowing piecewise linear maps, because that's what shows up in our equivariant neural network. Every vertex is a representation. Every edge corresponds to a convolution operator, something like this, an equivariant map. But don't forget the nonlinearity, so there's also some nonlinearity built in. That's piecewise linear representation theory, kind of the prototypical example. Okay, let's have a look at our that cyclic group. And to stay closer to the applications, I would like to have real representations. So let me explain to you the real representation theory of the cyclic groups. So the complex representation theory of the cyclic groups are very easy. The cyclic groups have a generator A, and this generator A maps to some root of unity, zeta, whatever. And for example, for the cyclic group of order 6, which is like the rotational symmetries of the sixgun, you have 6 choices. So you have 6 one-dimensional representations. What about the real representations? Well, as you can already see here, some of my choices are not real numbers, so this doesn't really make sense for real representations. But it's not much more difficult. It works as follows. So you just pair the one with its conjugate to get a new representation, which is really just mimicking this base change here. So over the complex numbers, you can decompose things. So this is a bar. So you can decompose it into a block matrix. But over the real numbers, you just have the corresponding rotation matrices. And I'm pretty sure you remember that rotation matrices look like cosine, sine, sine, cosine type thing. So you just do the following trick to get all the simple real representations. Yeah, simple, irreducible. Simple, by the way, I'm also always using the notion simple. Some people call that irreducible, just the elements of the theory. Anyway, so to get them the real ones from the complex ones is really easy. You just take the complex ones and you sum over the neighbors, whenever that makes sense. Some of them are already real, that's fine, we like them, so those two are good. And then those two form a two-dimensional representation, and those two form a two-dimensional representation, just using this trick here with a little base change matrix. So you always just take the sum of them, and anyway, now we have one-dimensional representation and two-dimensional representation, depending on the cyclic group you have. So here for the cyclic group of order 5, we take the sum of the neighbors. So here you have a two-dimensional representation. Here is a two-dimensional representation. Here's a one-dimensional representation. So note that, of course, 2 plus 2 plus 1 is 5. And for 6 here, it was, here's a one-dimensional, here's a 1. So it's 1 plus 2 plus 2 plus 1, which of course is 6. So some of them get two-dimensional, some of them stay one-dimensional. And there's this even-odd pattern, which really just comes from whether I have an even gun or an odd gun. The even gun will have 1 and minus 1 appearing. The odd gun will only have 1 appearing. So one of them has one-dimensional representation. The other one has 2 one-dimensional representations. But to get, as I said, to get from the complex to the real representations is really just easy. It's just this type of base change matrix between them. Hopefully that makes some sense. And I would like to study now the piecewise linear representation theory associated to these type of objects. Yeah, I hope that makes some sense. And let's just do it, right? So I will do it for you. And we can play live. I will pull it up anyway. So it works as follows. I will explain what I'm going to do. I'm going to illustrate a very high dimensional map. So the first illustration I have is a 7-dimensional map. In case you don't know how to illustrate a 7-dimensional map, you will see it. It's actually quite a nice idea. Anyway, I do the following. I have those simple representations, yeah? I have them according to how the 1 or 2-dimensional ones. And I include them into, let's say, the regular representation. Apply my ReLU component-wise. That's kind of what I need to do to study. I really just zoom in into one vertex of my equivariant neural network, and I have a very easy permutation representation sitting at every vertex, which is just a regular representation. I just zoom into one vertex, and zoomed into the one vertex, my decomposition problem looks as follows. I would like to study what this map does. So it starts with some simple representation. It includes it into, so let's say it includes it into the regular representation, applies ReLU, and then projects to the copies of the various simple representations. In particular, let's say I do this for n equals 5 when I start, and this one would be 2-dimensional, then I have a 2-dimensional thing here, so that's like a 7-dimensional map. And I will illustrate this type of map now. For you, will I just pull in my little illustration here, which you can run online. Let me just zoom in for you. Okay. So here's the setting. So n is n. Linear is, my activation function that I choose in the middle. I have several that I can use here. But most interestingly is linear and ReLU. Scale outputs is just making it a bit nicer, to look a little bit nicer. So here's my 7-dimensional map. And what you see now is Schur's lemma. So how do I illustrate a 7-dimensional map? Well, the output is the red point. And the input is my cursor. Yeah? So my cursor is going here. And this is like really simple. Schur's lemma tells you that in my little decomposition here, Schur's lemma, linear maps, remember I have linear maps, tells you the only map from Li that survives this thing is the one that goes from Li to Li. And because I've chosen my little linear map to be very boring here, it really is just the identity on those components, right? Very, very exciting. So this is just a 1-dimensional thing. So I only have one input vector. So I have a 5-dimensional output, a 1-dimensional space, a 2-dimensional space, a 2-dimensional space, and I have a 1 or 2-dimensional input depending on where my cursor is, right? So this is just a map from a 1-dimensional thing to a 1-dimensional thing, and it just follows nicely my cursor. So not that difficult. And ReLU gets a bit more interesting. So let's first understand that this is ReLU. So identity on the plus part and 0 on the negative part, yeah? So I'm not cheating. You can right-click vSource, and you will see that I'm not cheating. So anyway, so yeah, here's ReLU, right? Doesn't make sense that this is ReLU. And you can see it's the same as before. It essentially is the identity, but now the ReLU is sitting in between. Yeah, very, very nicely here, goes up and down. But now something interesting happens. The Schur lemma now says, you see it already. So now you have really a 7-dimensional map. This is how you illustrate a 7-dimensional map. So if I start for n equals 5 with a 2-dimensional representation, and I just have some input in this 2-dimensional representation, which is my cursor, as I said, then I have output in everything. So this is really a 7-dimensional map. And it's not quite, so this guy here will move with twice the speed. So let's test that. So I move it halfway around, and the other one already moves twice around. I move it another one, so just twice the speed. And this is just a little bouncing back and forth, and you can kind of see that Schur's lemma is wrong here again, twice speed, but now in the opposite direction. Excellent. So Schur's lemma is wrong. Let's go back to linear. Schur's lemma, nothing happens, everything just goes to itself. Piecewise linear, Schur's lemma is wrong. Ah, beautiful. It's so beautiful. And it's very addictive to play, by the way. So you can go to a higher whatever, something like this, and you can see here's ReLU. This is odd now, so you have another 1-dimensional representation, and you can already see that it's not, again, Schur's lemma applies, Schur's lemma doesn't apply, and now it gets actually very interesting here. So some very sophisticated patterns arise. So decomposing a neural network actually leads to those type of interaction effects, which I'm going to describe more carefully as we go ahead. So it's really a lot of fun to do this. For 27, for example. So here's 27. Oh yeah, by the way, 27 is a bit big. Let me go back to something smaller, like 10. So 10 is a 1-dimensional. 2, 2, 2, 2 is 8, and another 1-dimensional. This is how the count works. And here you can already see it's kind of interesting. So this goes here, but not to here, but to all the others. It's a very exciting. And if you go higher, it's a lot of fun to do this. 27, for example, it gets completely bonkers, and I can't really tell you what's going on here. This one here gets completely bonkers. Like, it's insane. Yeah, so the decomposition of those maps is highly non-trivial in this case, which kind of explains why neural networks are so interesting, because somehow representation theory is a bit kind of a boring type thing. And because there are constellations which shouldn't be there, and now there are no constellations, and even this around one neuron, remember, I'm just trying to do the decomposition around one neuron, you already have interesting effects for the cyclic group. I'm just doing the cyclic group here. I hope this illustration, I will come back to the illustration momentarily. Hope this illustration makes some sense. And I will record what's going on in a graph. I call this the interaction graph. The vertices are just simple representations for n equals 5. Here's the 1-dimensional, here 2-dimensional ones. And whenever there's a non-zero map under ReLU, or whatever kind of my favorite activation function is, I put a little edge between them. So let's see whether we can understand that actually. So here's my interaction graph for n equals 5. So I have 3 vertices corresponding to the 3 representations. This one, the trivial one, only talks to itself, so I only draw a little loop. And this one talks to everything, including itself, so I draw a little loop and a map to everything. And similar here. So let's see whether this makes sense to you. So here is 7. For 7, I should have 3 that talk to everything, and then the trivial representation. So 3 that talk to everything, and the trivial representation that only talks to itself. Trivial representation, very mean, only talks to itself. I hope this makes some sense. So I have this graph, and the graph encodes how there are non-zero maps between them. Kind of the measurement of difficulty. A lot of ingoing edges means it's hard, because you kind of can't ignore it, because everything kind of wants to factor through. So trivial representations, in this sense, are really difficult representations. They have a lot of in-pointing edges. And that's, by the way, true in general. So here, you can easily do them with a machine, and they're here on the website actually. So if you go to order, So these are my three representations for n equals 5. And the order is you send the generator to a matrix of a certain order. So here the matrix is of order 1, here the matrix is of order 2, and this is how the graph looks like. I didn't, whatever, we can go to 14 and the graph will look like this, for example. I clicked on dimension. I should have clicked on order. So the order is, so here order 14, order 7, order 2, order 1. So let's go to 13 maybe. Not 12. I wanted to go to 13 actually. Let's see. 13, here you go. So you have this huge connected component at the top where everything talks to everything, and a little component at the bottom. And let's see whether we understand the theorem. So for ReLU, it works as follows. Every vertex has a loop, yeah, fine. And there's a non-loop edge from L to K if and only if the order divides the order. So let's have a look again at the graph. So 13 to 13, yeah, the order divides the order, and 13 to 1. So maybe 13 is a little bit boring. Maybe let's go to 15. 15, so 15 has an edge to 3 and 5, but 5 has no edge to 3, and 3 has no edge to 15, but only to 1. Similarly, 3 has an edge to 1, but not to 15 or 5 because of the division type thing. Yeah. So maybe I should go to a little bit of a smaller thing like 9. 9, you have the 9 ones that map to everything. The 3 one will only map to the 1. And it's kind of how they divide one another. And there's only one thing that you need, and it's really nice results. So the higher orders are easier, and they always project to the lower orders. In particular, the trivial one has a lot of ingoing edges. And this is essentially true. Just in the even case, you need to divide one of them by 2. So 8 will not point to 8 because you need to divide one of them by 2. No, fine, but otherwise it's the same. You kind of point to all the divisors under this order operation, right? So order prime is really same, but divide the order by 2 if even. Just what happens. But essentially you can ignore that, and it is, you get an edge if and only if the order divides the other order. In particular, higher orders point to lower orders. High orders point to low orders, right? So this is kind of what's happening here. And now you have this neural network, you do this decomposition, and the high frequencies point to the low frequencies. Or the other way around, depends a bit how you say it. Anyway, so here's absolute value, kind of same thing, but now you get rid, absolute value is a lot of fun. So let's actually have a look at absolute value. So here ReLU, and now absolute value is kind of this fun thing. Looks very similar, but for example for 8, it kills the identity component. Absolute value is completely bonkers. It kills the identity component, and yeah, for some of them, it kills the identity component on the corresponding thing. So otherwise, it's very similar to ReLU. So in the graph, looks very similar. It just had principle, doesn't need to have loops, but otherwise, it's the same type of graph. And you could find that one here as well. Maybe down here, you can go to order, and we can go to maybe whatever, something like 8. Then here you can find the graph. So no loops at 8, no loops at 4. If you go to 10, then you will have a loop at 5, but no loop at 10. It's again an even odd thing. But otherwise, it's exactly the type of ReLU graph. I mean, you can actually prove that. And just for comparison, the graph for linear is just trivial. That's Schur's lemma. Right? There's just vertices but no edges. That's the linear graph. So kind of this graph measures the complexity jump from the real thing you want for neural networks and the linear world that people like to study in representation theory. Hope that makes some sense. Yeah, and why would you like to do that? Why is this capturing the complexity? Well, let's say you have neural networks, kind of a lot of those in a row, like a really large composition of matrices, and now you want to decompose your network and compose the corresponding pieces. So let's say around the vertex you have something like this graph, and now you have two of them in a row, and you can already see that the amount of information you need to evaluate really depends on whether you have something like with a lot of ingoing edges or something with few ingoing edges. So if you really want to evaluate your neural network on L1, you could simplify the calculation drastically. But if you want, because you just have one pass, and now you would have one pass even if there are like a million in a row. But if you want to go to L0, well, you kind of have still this kind of the same type of a lot of pass. So kind of where they are in the order of this graph tells you whether you can easily split them off from the calculation of the neural network, how much they will contribute actually to the result. Kind of this hierarchy on this Schur lemma type thing tells you how important the contribution of the simple representation is for the result of your neural network, if that makes sense. Okay, and just to make sure we understand how those maps look like, it's actually not loading. Let's ignore it. We can do it. We can do it here. So how they work, what is a nonlinear map? So let's say for C4, a nonlinear map, a piecewise linear map that is equivariant. Well, the action here goes as follows. It just turns it around. And all I'm saying is that all points are of the same height. And it looks like this bouquet of a flower. Like here's a contour plot, right? And the action goes from here to here to here to here to here. So this piecewise linear map is clearly C4 equivariant. And you can also see why there is no, and this is a map from two-dimensional representation, which is the bottom, to the trivial representation, which is the third coordinate, which is a three-dimensional map. And you can clearly see that you can't have, you can't have a linear map, because a linear map would be a plane, and on a plane you just can't turn it around in a Z-mod 4 fashion, right? But on a piecewise linear map, if you bend it up, you can actually nicely turn it around. And if you go from a two-dimensional representation to a sign, the same thing happens, just the sign swaps, right? It has this up-down type pattern, but you can still kind of move around in the Z-mod 4 fashion. And this is exactly why there are so many more piecewise linear maps, because you can't do this game with equivariant piecewise linear maps, because you cannot play this game with just a plane. And that's the reason why piecewise linear representation theory is so much more exciting than linear representation theory, right? In this case, this little flower has clearly a Z-mod 4 symmetry, but it's also obviously not a linear map. And this is why there are so many more things. Anyway, here's some general facts that work for any finite group, not just cyclic groups, but anyway, we just discussed cyclic groups in this video. So I think it's a very nice question to write down those interaction graphs for other groups. I haven't done that. Just for dihedral groups, cyclic groups. For cyclic groups, I showed you the answer. Dihedral groups are similar, and a little bit for symmetric groups. But it's kind of a nice research question. Anyway, something you can answer in general, for example, is that either your space is 0 or it's uncountably dimensional. So the notion of a dimension gets a bit fishy here. Piecewise linear is really doing analysis, so everything is very, very large usually. So you shouldn't talk about dimensions. And it holds for arbitrary group, and the proof is not very difficult. Essentially, you just think of this picture of rotating, let's say, by Z-mod 4. So you only need to determine what's going on one slice and then just rotate it over. Very similar to in this picture here. And now what you do on this slice is you can do whatever you want. You just rotate it over, so you get uncountably many different maps. And you can just rotate around the Z-mod 4 symmetry. Also, Schur's lemma is maximally false in the following sense. So you have a non-zero map if and only if the kernel of one of them is contained in the other. By kernel, I mean the ones that act by the identity matrix. So it's a representation, the kernel of that action map. So in the picture from before, this was just given by the order. The faithful ones, the one with high order, always kind of map to the non-faithful ones. This is just what happened in that picture. So the less faithful your representation is, the lower it sits in the hierarchy the more difficult it is to split off the more important the contribution to the neural network. So faithful things usually have a small contribution to the neural network. And then you can write down the various interaction graphs, and it only takes, there are only 3 states, and I showed you all of them. So the one for the linear map is boring. It's just the non-connected thing. And this really corresponds to Fourier theory. Like linear representation theory is like Fourier analysis of sine, which is boring, obviously. So if you do Fourier approximation of a sine, you don't get anything. And piecewise is more like the Fourier approximation of ReLU applied to sine. So ReLU applied to sine cuts it off like this. And if you then do the Fourier approximation, you will see that you have higher and higher frequencies that have lower and lower contributions to the problem. It's exactly as in the theory from before. The higher and higher frequencies are the higher order representations, and they have lower contributions to the corresponding problem. So what I really showed you is kind of a version of the Fourier analysis principle applied to a neural network just in terms of representation theory. So I've done those as well, and you can find more details on exactly the same website where I was playing my little piecewise linear game. Anyway, I hope you enjoyed this video, and I also hope to see you next time.